Okay, we're going to look at number 13 from exam 1. Oops, exam 1 from 2014. The question asks, predict which compound in each pair will be higher in energy. Circle it at 1 point, and then give a short answer why for each 2 points. So the first one shows a cyclopentane and a cyclopropane. So the cyclopropane is going to be higher in energy. And the easiest way to think about this is to think about bond angles. Right? All of these carbons in the cyclopentane are what hybridization state? What hybrid state? That's the geometry. What hybrid state? sp3, right? And they're tetrahedral. That's right. They're sp3 and they're tetrahedral. What's the bond angle associated with a tetrahedral or sp3 hybridized carbon? 109.5. All right. In the cyclopropane, what are the hybridization states for all those carbons? Also sp3, right? And they all want to be what bond angle? 109.5. So essentially at this point, at a 5-membered ring, that's like the last point where you can get this bond angle. So it's happy, right? So it's not too sharp, right? The problem is with a cyclopropane, what's the bond angle from here to here? 60, right? If it's equilateral triangle, right? It's 60-degree bond angle. That's going to make it highly strained, which means the orbitals, right, between this carbon and this carbon aren't going to be able to overlap that well because they're pulled so tight, right? So those bonds are going to be not as strong, more reactive, right? So they're going to break. They'll be more likely to break. They'll be higher in energy. So it's all about the bond angles, right? In the middle one, right, if you had a cyclobutane, right, what's the bond angle of a square? 90, right? That's again obviously less than 109.5, so that wouldn't be as bad as a cyclopropane, but right, all it does is tell you that these bonds, right, aren't as strong or more reactive than these bonds. It's not to say that cyclopropanes exist, cyclobutanes exist. They're just going to be more reactive, but they're possible. It's not that they're impossible. It's just they're more reactive. Right. So for our problem here, we're going to work on doing nomenclature for all different types of groups we talked about. So that would include just plain alkanes, alkyl X's, alkyl-halides, alcohols, amines, and ethers. So let's start with alkyl-halide or alkyl group first. Let's zoom in on that. Get this away. Zoom in here on this. Over there. The first step here is to find the longest chain, right? The longest chain. So what's the longest chain here going to be? Anybody have an opinion? 5. So that means it's going to be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Hope I didn't paint myself into a corner here by drawing this. The root name is pentane, I guess, to start off with. This is what happens when you do things on the fly. Pentane. How do we want to number that? Anybody have a idea? How do we want to do it? Start from the bottom to the right and say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Does it matter? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Does it matter? I'll just pick one way. A lot of times there's maybe more than one way, but I'm going to go this way. I'm going to say 1, 2, 3, 4, 5. Does that seem right to everybody or not? Yeah. That's one way? Okay. So I circle it. Right, I want to number it such that the substituents, I always want to have, right, the lowest number, first substituent, lowest numbers possible. Right, it's not a total group, it's just whatever is lowest possible, so that's why going this way it could have worked too. But this way has less substituents. If I go 1, 2, 3, 4, 5, I'd have 3 substituents. So you want to have less substituents. That's a fine rule that you may or may not know. It's okay. So how do I name this stuff? So I have pentane. What are my substituents I have off this thing? I have a methyl on 2-methyl, right? And what's off carbon 3? What's that called? Isopropyl. 3-isopropyl. And does I come before M? So it's 3. So the answer should be 3-isopropyl, 2-methyl pentane. Usually when we do nomenclature stuff is worth 2 points each one, and if there's one little mistake, we'll take 1 point off. But if there's more than 2 mistakes, if there's more than one mistake, then you don't get any points. So if you put the alphabetizing wrong, it'd be minus. If you would lose, you'd only get 1 point.
I mean, if we were like 3, if we went the down from like top right to like bottom left to make that.
This way?
Yeah.
It'd be fine. I wouldn't give you one like this. This is what happened when I made up on the fly. This is probably the best name though. All right. So let's go over to the alkyl X now. Well, the alkyl X, what's its parent chain going to be? How many? 4, so that would be what? Butane, so its parent chain is going to be a butane. So it's certainly, this. All right. So what does that mean? Which way should I number first? Left or right? Who gets priority, iodo or chloro, do you think? If you had to guess, what will be the order? So, how do we decide what's number 1? Alphabetizing, right? It's kind of the theme of nomenclature is alphabetizing. So, chloro, C comes before I, so this would be 1, 2, 3, 4. So how are we going to name this? We have a 1 chloro. We have a 2 bromo. We have a 3 fluoro. And a 4 iodo, right? Now we just got to put them in alphabetical order. Not by the order of the numbers, alphabetical order. So the number, what would the alphabetical order be? 2 bromo, 1 chloro, 3 fluoro, 4 iodo, butane. Make sense? All right, let's take a look at this alcohol. There's 2 ways you can name this right off the top of my head. Remember, every molecules can have more than one name, but every name only represents one molecule, right? So I can have multiple names, right? You can call me Dr. Wenzel, Professor Jerkface, all sorts of things, but that still means you're talking about me, right? So molecules can have more than one name, but every name only means one molecule. So what's the name of this molecule? There's 2 ways you can do it. There's a common name, and there's an IUPAC name. So let's just do the IUPAC name first. What's the parent chain? Propane. All right. Now it's is it propane or propanol, right? Because it's an alcohol. So you say propanol, the OL, right? Now you need to tell, are all propanols the same? Because what kind of propanol is this? So 1, 2, 3. This case it's 2 propanol, right? So you have to say it's on the second carbon. You could have said 1 propanol as well. Then I already heard the common name. Someone said, what's the common name you could call this? Isopropanol as well. Either name would be acceptable, right? Because this is an isopropyl group, right? When something's off this in the second position, that's an isopropyl alcohol, isopropanol, or 2-propanol would work as well. All right, now we're doing amine. All right, it's a mean old world. So what do we want to call this one for our parent chain? What would our parent chain be here? So in the amines, you want to find the longest, the most substituted group off the nitrogen. And so what's that going to be here? isopropanol or propanol. So you could say you could call this the root name is going to involve this, right? So you could either call it the parent name could be isopropylamine, or you could say 2-propylamine. Those are the parent names, right? Those are the parent names. So either one works. Then the next part you need to, right? How do you distinguish these two things, the other things off the nitrogen? How do I tell somebody something's off the nitrogen? And I say what? N, right? So in this case, you have two things. What are they? Methyls, right? So you say dimethyl, and instead of putting a number, you put NN, right, to indicate they're off the nitrogen. So NN dimethyl 2-propylamine, or NN dimethyl isopropylamine. Either parent name would work. Be fine.
What was the combination?
NN dimethyl 2-propylamine or NN dimethyl isopropylamine would be fine. So our last one is an ether, and this is MTBE. So one of the things you should have known from lab, I wouldn't do this to you on test, right? I'm not testing you on the lab materials, right? But just because we're here, let's talk about it. So what does MTBE stand for? Methyl tert-butyl ether. So we know we have an ether, so put an oxygen there. And we know we have things off the ether, right? Because ether has 2 carbons on either side, right? So when you name an ether, right, methyl is off one thing, so we put a methyl on one side, right? So we know one side of the ether is a methyl. Tert-butyl you might not know. Tert-butyl's the pitchfork. Butyl, so it has 4 carbons, right? So this is what a tert-butyl group is. You don't know that yet. We haven't got there, but we will. So the only one that really is weird, that a common one you know, should be isopropyl at this point. Tert-butyl is a new one. We'll get there. But that's how it's named. Methyl tert-butyl ether. Okay. So let's do a ring flip. So I just drew a chair structure of just some random molecule, and we're going to do a flip.
Is there anything on?
So we're going to do a flip. So the first thing you need to do is I would just start arbitrarily numbering carbons, right? I'm not naming here, so you don't need to worry about what number 1 is. Don't worry about that. I mean, you could, but we're not going to. I like to put the top right one, number 1, 2, 3, 4, 5, 6, and it's a ring flip. So that means carbon 1 is being pulled down, right? The top of the headrest is going to get pulled down. The footrest is getting pulled up, right? So we're here together, and shoom, right? It's not really a flip as much as it is just a quick conformational change, right? So that means now our chair is going to lean not to the right, it's going to lean towards the left, right? So we draw a chair like that, 2 parallel lines, parallel lines, parallel lines, parallel lines, parallel lines, right? We know where did carbon 1 end up? It went pulled down, 4 went up. So let's label this as 1. This is 4. Right. That means this is 5 and 6, 2 and 3. Also notice in here, right? Is there an axial position is there an equatorial position on carbon 1? There is. I just didn't draw it in. Right? There's an H there, I just didn't draw it in. That doesn't just because right? Only thing I left out here was what? I left out H's. That doesn't mean they're not there. They're still there. Right? So if something was up, right, where's it going to be on the ring flip? Is it going to be up or down? Up. If you're up, you're always up. If you're down, you're always down. Only thing that changes on the ring flip is whether you're axial or equatorial. Right? So if you notice actually on this ring, what would you say about all those substituents? What are they to each other? They're all cis. They're all cis and they're all up as I have it drawn. So when I draw this here, they all better be cis and up. But are they all going to be equatorial then? Is that what that means? No. Right? Up and down is different than axial, equatorial. Right? These are all up. That means on the ring flip, they all better be up. But if it was axial and the ring flip is going to be equatorial. Good. So for instance, for carbon 1, there's a chlorine that's axial. Now it's going to be equatorial and up. Carbon 2 had a fluorine that was equatorial. Now it's going to be axial and up. Carbon 3 had an isopropyl group that was axial and up. Now it's going to be equatorial and up. Good. 4 had an iodine that was equatorial and up. Now it's going to be axial and up. And 6 had a bromine that was equatorial and up. Now it's going to be axial and up. Good. Which one? You could draw the hydrogens in. If you want to draw the hydrogens in, absolutely you could do that. That wouldn't be wrong. Right? Absolutely, it'd be fine. I just didn't do it just for ease. Now, take it another step further. Which ring conformation is more stable? Would it be A or B? Which one's going to be more stable, you think? No, well, let's look at the difference. What's the difference between them? Let's just look at the differences. So A has two things axial, right? A has an isopropyl and a chlorine axial. B has an iodide, a bromine, and a fluorine axial, right? So easiest thing to think about is two things axial versus three, right? Things that axial, that's bad, right? Especially if they're cis, right? They're all up in axial. They're all running into each other. They have those 1,3 diaxial interactions. And plus iodide's huge. Bromine's huge, right? That's bad, right? So even just looking at 2 versus 3, but even if it was just these two or those two, I would probably say B is going to be higher energy, a higher energy conformation.
That's the main rule, is that if they're axial.
The axial things, yep. Not just axial, but axial on the same side, right? So it's not just about being axial. I mean, being axial is bad, right? Because even if there's a hydrogen here that's axial that you can run into, but if all these groups are axial on the same side together, that's for sure bad. Okay, so here we go. We're starting with this Newman projection, and what we're going to do now first is we're going to do a series of rotations. Come on with me. But we're going to start rotating it, and then once we rotate it all the way 360 degrees, we're going to draw the free energy diagram where they land, right? The potential energy of all these. All right, so we're starting off this way. Let's just move in this case, let's move the front carbon. This carbon right here is where we're going to rotate. So if I want to rotate 60 degrees, I'm going to say clockwise, or big C, clockwise. So that means I'm going to rotate this H here, this H here, this H here, right? A circle has 360 degrees. The degrees between here and here is 60, right, approximately. So we'll rotate 60 degrees clockwise. We're moving the front carbon. Just move the front carbon. Right? So, what didn't change? The back part didn't change. So I always like to fill that in first, right? If something didn't change, don't change it. So now I went from a staggered conformation, right? This is staggered, and now this H is over that H. This H would be, I'm just going to extend it down there, on top of that isopropyl, and the methyl will be over there, right, rotating 60 degrees clockwise. I could do this again, rotate another 60 degrees clockwise. So I went from staggered to eclipse, now I'm going to go back to what? Staggered, hopefully. So again, what didn't change? The back, don't mess with it, just draw that in first. There's an H, there's a methyl, and there's that H. Alright, if I rotate, this H would go there, this H would go here, this methyl would now be there. Alright, continuing on. 60 degrees clockwise, again moving that front carbon. The back didn't change, leave it the same. Again, we went from staggered, now we're going to have what? Eclipsed, There should be H here and an H here. Should we do another 60 degrees? What didn't change? Back carbon. Went from staggered, or went from eclipse, now we're going back to staggered, H and H. Of course, 60 degrees clockwise. Making room for myself. Do another 60 degrees, why not? Why stop now? Can't stop, won't stop. Back carbon didn't change. It was staggered, now it's going to be eclipsed again. I think we are now officially all the way around. We've made it. And then if we did another 60 degrees, we'd be back to where we started, 60 degrees clockwise. Good. Okay. Everybody square with that, how that went? So now let's label these with some letters: A, B, C, D, E, and F. Let's shrink some more up. They're going to be mad at me. Which one's going to be, so the easy way to do this is which one's going to be the highest in energy, which one's going to be the lowest in energy. Which one's going to be the lowest in energy? A, B, C, D, E, or F? C. I like C. C puts the methyl and the isopropyl as far away from each other as possible. Right? So you should have been able to eliminate some of these, right? Low energy, you knew it couldn't be what? If it's low energy, it had to be either A, C, or E. It had to be a staggered conformation, right? Had to be staggered. And then you looked at the staggered ones and say, well, here, this isopropyl and this methyl are gouged to each other, or 60 degrees away from each other. They are here too. Here they are 180 degrees away from each other. That's as far away as you can be from each other, the two big groups. So that would be the lowest energy. So C would be the lowest energy. So if I was drawing a little chart in this bottom right corner, right, and this is PE for potential energy, C would be down here, right, low. Be low in energy. Right, so potential energy, if you're high up on the chart, that means you're high in energy, you're unstable. So which one's going to be the highest in energy, do you think? If C is the lowest, which one's going to be the highest? F. F would be the highest. Right, that'd be the highest in energy. And now we could fill in along the way. If we had E and so what about E and A? Where are they in relation to each other in energy? They would be, E and A would be the same, right? They're both staggered and they both have the same type of interactions. And then what about B and D? Same deal. They'd be the same, but they'd be even higher yet, right? B and D. So now this isn't a flow chart, right? So be careful. It's not that right? They've showed you in the book where you start with A and you would have gone up and down, all that kind of stuff. All this is just relative, right? So I'm saying C is the lowest, E and A are the same because they're both staggered. B and D are both eclipsed, but they don't have the worst eclipse interaction of the methyl and the isopropyl on top of each other. That's F, and that's why that's the highest in energy. We see that difference there, how I'm showing it? So there's nothing on the x-axis. There's nothing here. All we're worrying about is potential energy. So it's ranking them by potential energy. Okay? All right, so first we're going to do a quick naming problem, and then we're going to turn this into a Newman projection problem. So what's the name of this? What's the parent chain going to be? Ethane. Ethane. And actually it's going to be ethanol. Right? So the alcohol takes priority. The alcohol is the substituent group that matters the most. So that would be 1 and that would be 2. So we could say ethanol, which it's assumed is 1. And we need to say 2-fluoroethane. ethanol, right? I'm not going to be, neither of us will be mad about your dashes or your commas. I mean, try to make it reasonable. Like, don't celebrate with like a semicolon out of nowhere, but like, I'm not, you know, I can't spell very well either, so.
So is it wrong if you put the 1 in there or no?
You don't have, if you put the 1 in there, that'd be fine. You don't have to, but you could. You don't have to, but you could. Okay, so 2-fluoroethanol. Now let's work on transposing this to a Newman projection. So I'll even draw a Newman projection for you to start in a staggered conformation. And pretend we're looking down from our eyeball. Let's do the other way. Let's do from C1 to C2. So, or C2 to C1. So this front carbon right here is C2. So see if you can transpose that Newman projection. Okay, so we've successfully named 2-fluoroethanol, right? So we did a naming problem. And now we're looking down C2 to C1. So that means our front carbon is C2. The biggest mistake people make on these is they forget what is bonded to carbon 2, and they forget to put it on there, or what's bonded to carbon 1. So what is bonded to carbon 2? A fluorine and 2 hydrogens. A fluorine and 2 H's. So one thing you can do, right, feel free to draw in the H's. Nothing wrong with drawing them in. We probably won't provide them for you. I just said a fact. That wasn't a hint. That was it. We will not provide hydrogens for you, or possibly lone pairs. You get to bring your own. HYOB. BYOH? BYOH? Yeah. You can tell how much fun I had in college. Right? So what else will we do? Is that right for carbon 2? Yep. So what's on carbon 3, or carbon 1 that we need to have on there? An OH and H's. Does it matter where I put them at this point? It doesn't matter at all. Right? If I had wedges and hatches, then it absolutely would matter. But notice here, we don't indicate the stereochemistry. We don't indicate that there's wedges and hatches. So you can put it anywhere you want to. If I did put the wedges and hatches, you would have to know how to do it. And we can do a problem like that. Yes. How about we do this? How about we do this? The way I have it drawn here, how about I convert this into a wedge and hatched? For the way I have it drawn. Right. For exactly the way I have it drawn, I'm now going to convert this, for my next trick, I will convert this into a wedge and hatched model. All right, so now I'm going, this is equal, right? Equal sign, or whatever. So the first thing I'm going to do, I'm going to draw a straight line, and I'm going to say carbon 2 and carbon 1. All right, so if I'm looking at this as carbon 2 right now, what do I have straight up? What do I have? An H, right? So that's going to be where I put an H right here, right? It's not to my right or my left, it's straight up. What's to my left and down? Fluorine. So I should draw that with a wedge going down, right? Because it's going away. Right? If I turn myself, what's to my right and down? The H. So that would be wedged and coming out at me. Now if I go back to carbon 1, what's straight down is a H, so that's right there in the plane. That's in the plane. What's up and to the right? OH, so that would be wedged or hatched?
Wedge.
Wedged. If you got confused on that, one thing you look at, this H and this OH are on the same side. This H was wedged, right? So that means this OH has to be wedged too. Right? If we're looking at it, they're both to my right. This other H is going to be hatched then, up and to my left. So you should be able to go from either or, back and forth to these. Build a model. Build a model. You have your model kits with you. Build a model. Right? Build a model. The easiest thing to do to make sure you don't mess it up. So doing taking a name and then converting it to a flat structure, a planar structure, and then also converting it to a chair structure because it's cyclohexane. So in this case we have cis, 1-ethyl, 4-methyl cyclohexane. First thing you need to be able to draw is just a cyclohexane. arbitrarily make this carbon number 1. So that's 1, 2, 3, 4, 5, 6. It's 1 ethyl and it's 4 methyl. And it says they're cis, so you could draw it with both of them being wedged, or you could draw it with both of them being hatched. Either way is fine. Right? Cis. 1 ethyl, 4 methyl, cyclohexane. Right? So you could decide they're up or down. I'm not technically telling you that with this name. So let's turn them into a chair structure. At least draw one of the chair conformations, right? Because there's always 2 chair conformations, right? You can always do a flip. There's always 2. So let's do 1. I like to make this carbon 1. So I'm going to make it 1 ethyl. That means if this is carbon 1, 2, 3, 4, 5, 6, drop a little better. Is the methyl going to be equatorial or axial on carbon 4? Axial is right. Good. Because it has to be what? Down. Right? I arbitrarily drew this equatorial and down so that whatever happens next, this has to be down too. Right?
Do you really draw that into like hydrogens? Could you just put, how do you signify that was your method? You just put CH3? You don't
Yeah, so I don't need to put a CH3 to tell you this is a methyl. If you see something like this, a bond coming out like that, that is a carbon.
Right.
You could write CH3 here if you want to. There's nothing wrong with writing CH3 in. But you should recognize this as a methyl.
No, I did. I just like,
Yep.
you draw on all the other lines.
Yep. And then, of course, right, if you wanted to draw in your H's, you could. There's an H. There's an H. And there's an H. It doesn't tell you, right? It doesn't tell you if it's up or down, right? That we'll learn in Unit 3 about enantiomers, right? Molecules have handedness. So that it does matter. It's just not indicated here. So, all right, let's talk a little bit about things that affect, let's say, I'm going to say boiling points. It could also be melting points as well. All right, in order of importance, van der Waals. Right, van der Waals interactions. The more van der Waals interactions you have, right, the higher your boiling point is going to be. So, classic example is straight change things can stack up, whereas things that are more branched, right, will not be able to. Those are van der Waals interactions. Those are the weakest interactions. Right?
Wait, this is the weakest?
Yep. Van der Waals are the weakest, right? These are all IMFs, intermolecular forces. And van der Waals is the weakest. The next, there are dipole-dipole interactions. Now, you notice in van der Waals, right, there's no polar covalent bonds here. Dipole-dipole means now there's going to be some polar covalent bonds. Good example, diethyl ether versus just hexanes. Right, diethyl ether is going to have a higher boiling point than hexanes because right now it has polar bonds. So it has a part of the molecule that could be delta minus and a part that could be delta plus. Whereas for the hexanes, it's all delta nothing. It's not polar. Right? Right? Don't write that down. Delta nothing. Right? And then the final, the most important intermolecular force, which is of course a force, not a bond, hydrogen bonding. Right? Hydrogen bonding. That requires the molecule itself to have a polar bond to hydrogen. Not just any polar bond like here, but an actual polar bond to hydrogen. So you could have things like alcohols versus an amine. Which one of those has a higher boiling point? Why? Oxygen is more electronegative. That's a more polar bond. It's going to be a more polar interaction, greater hydrogen bonding. Good. So those are the 3 things that affect boiling points or melting points or any of those kind of forces.
So you said like the hydrogen bonding on the left.
Mm-hmm.
That'll be strong represented more like a positive
Right.
characteristic, even though there's more hydrogen bonding.
Even there's more, I mean, right, to be fair, I should probably make this, right, to make it all fair, I should make that a methyl. So it's, right, because I don't know if a primary amine, because it has two H's, might be different. So it would have to be 1H to 1H, and OH to an NH, 1 to 1. Because sometimes if you have two NHs is more than one NH, right? So I have to make it fair, I have to say there's a methyl here, not another H. Great.